What I want to talk about today, if I can find my tab, is I want to talk about build environments. And build environments are actually pretty, there we go, are pretty important to most open source projects. One of the things that I want you guys to kind of keep in mind as we talk about open source is, in general, open source is not somebody in a company standing there telling you, here is how you're going to do it. There's some of that. Some of the major open source companies actually do pretty well by being essential to projects that are used commercially, and so people on those projects, on those commercial projects, actually get paid time to work on open source contributions. Certainly, when I was at GE, and then again when I was at Kitware, and SimQuest, another company that I worked for who was doing open source, that was part of the norm. We were expected to develop stuff, to push it out to open source, and that open source was the core of what we would use to build our applications. I want to kind of differentiate this from the open core model that Patrick Masson was talking about. In this case, the open source was not just something that was hidden inside the projects. We would give you the open source. You could do anything you wanted with the open source, and then we would custom tailor applications using that open source based on the needs of our customers. And whenever possible, we would try to convince them to open source their solutions as well. And in every contract, we had the ability to pull out things that were essential, that were not essential to their program flow, but were essential to the development of the open source tool themselves, so that we could put that back into the open source, even if it was developed under their funds. So, it's good to make money off of open source from the standpoint of, we don't have a shortage of cows because cows are tasty, at least for those who are non-vegetarians. We don't have a shortage of carrots either, for much the same reason. But other types of foliage and fauna disappear if there's not a way to make them viable or make them useful. Certainly dogs and cats are rampant, whereas some less cute, more dangerous animals are not as common anymore. So anyway, on to build systems. These slides, by the way, were Bill Hoffman at Kitware was the originator of Cmake. It happened back in the early 2000s, if I'm not mistaken. It was used to build something called ITK, which we'll talk about a little bit, hopefully in the CI/CD section, although I may be reworking that a little bit. But Bill was really into parsing, and one of the complaints you'll see about Cmake is that rather than use an already established language and use a parser for an already established language, one of the biggest complaints against Cmake is they actually invented their own language. And I share that complaint. I think that it would have been much more powerful had they gone with something less arcane, less unique to Cmake. But Bill was one of the founders of Kitware, and they hired Brad King, somewhere in the 02 to 04 time range, while he was still working on his PhD, and he kind of took over the development of Cmake under the tutelage of Bill. And he was the originator of these slides and presented this for many years until he got tired of being asked to come to RPI once a year to give the slides. So I'll give him instead. I got his permission to license it under CC BY. So we actually jumped through some hoops to make sure that this was okay. And let's start out with our introduction. Okay, so a couple of things in the reference material, and you will want to have these on hand for the test. Let me pop these up a little bit. So the couple of things, this one I found kind of interesting if this actually goes. This is an overview of build systems. Now, when you're talking about build systems, I'm mainly going to be talking about C and C++. Most of my career was in C or C++. Only recently have I become kind of associated with Python. It's a cool language. I still like to do most of my stuff, most of my heavy lifting in C and C++. But you should read through this. Make is a generic Linux kind of thing. GNU Make in particular, that allows you to formalize and capture relationships. The middle third of our talk will be about Make today, but it's pretty common. Auto tools is basically it's kind of a predecessor to I'm going to call it a predecessor to Cmake and other meta build tools, in that it allowed you to go through and introspect your system and set up, write one set of auto tools that would allow you to build your code on a large variety of systems. So, it wouldn't matter whether somebody was running Ubuntu 18 or Ubuntu 16 or RHEL, Red Hat Linux. It was just a way to kind of let you set that up. And it's been kind of, I think that it's been overshadowed by more common, by newer utilities now. I haven't used SCons, but Premake is a lot like Cmake. And then there's Cmake, my favorite build tool of the last 15 years. Now, this is 2 years out of date. I think this is from 2018. Anyway, just read through this. Make sure you understand this. Here's the main criticism. It's improved. Still, that initial decision to not use something like Lua or another established language for which there were parsers, it does mean there's some arcana. And then Ninja is kind of a replacement for Make. Anyway, go through that, read that. I'm going to be most interested in Unix makefiles, so here's a makefile tutorial. We will talk you through some of the stuff, but certainly there is a lot more to learn. One lecture on Make is not going to make you an expert, but that and reading through the makefile tutorial may. And then here is Cmake. And we're going to talk about the relationships of all of those and kind of how they work together. But let's start off just by talking a little bit about what a build system is. So the whole concept here is that you have code, and the code is written in a way that is easy for you to understand, but it's not written in a way that's easy for like the computer to understand. So what we want to do, the goal of a build system is, the whole reason we have build systems is it takes the stuff that we write that makes sense to us, gets sent through the build system, and what comes out is something that the computer can actually execute. Now, it gets really easy when you start off, right? We're going to focus on C and C++. You should have had, your 2000 level, your 1000, all your 1000 levels and your 2000 level courses by now. So you should be aware of the differences between interpreters and compilers. We're going to focus on compiled languages for this particular exercise because, that's mainly where these build systems come in. Although in some sense you could think of the entire Python environment as a build system to support the interpreter, to find out the tools you're using, etc. But we're going to focus on just the C and C+ types of languages. There's a lot of languages, compiled languages, that fit this model. So it's a good one, and as you get into more and more software, you're going to find out that, the core of your programs generally end up being written in one of these compiled languages for speed and other reasons. Let's pop that up. Let's start off with a simple file. And by the way, I killed my, I did this all last night. I think it all works, but I did kill all of my my windows and everything, all my directories. So we're gonna, have to do this again from scratch, which is not a bad thing. And we'll start off by just saying, let's create. I'm gonna make a directory garbage. I know that if I name something garbage or junk or garage, that's the stuff that I can kind of delete without having to go in and think about it. But we can start off with a file, let's say hi.c, hi C, and we'll do our standard makefile thing, or our standard hello world thing, right? We just come up with a, see if this works. Yeah. So we just come up with a simple little program called hi. I don't like the okay, so I'm being pedantic here, but I didn't like the organization. That looks a little bit better, right? It's just a simple little program. It reads in standard IO as an include file, just to tell us how to do the print function. Int main, print out hello, return 0, and that's pretty simple, right? So we want to run this through a build system, and the build system is going to be, for this example, we'll do CC. I'm not sure why throughout the notes we switch between CC and GCC, given that CC is now aliased to GCC. But let's just kind of do this for now, right? So this just says take the file hi.c, compile it into something the world can understand, or the computer can understand, and then name the output file, the resulting program that we can run, hi. And if we hit return on that, it will do the compilation. I didn't make any major errors, and we can do /hi, easy, breezy, cheesy, pretty simple. But there's actually more going on here. Oh, and by the way, let me just take a look at this. So if we do ls-la on CC, sorry, on, you guys know what the which command does, right? So the which command tells you when you have multiple possibilities, which possibility you're actually using. So it'll search your path and find what program you're using when you type in CC. So if we look at CC, we find out that CC is actually, the one we're using is user bin CC, and that's actually linked to etc/alternatives CC. So we can do ls-la, so there's a soft link there, ls-la/etc/alternatives CC, and that links to user bin GCC. So if we do which GCC, we'll find out that that's the GCC we're using. So GCC and CC are the same, and we can kind of keep going down through here. Digging deeper and deeper until we find out that user bin GCC is linked to GCC 9, and let's see if this works. And GCC 9 is linked to x86-64 Linux, right? So we can pop that in, x86-64 Linux, GNU GCC 9, right? Which finally doesn't have a link. So no matter what we type, CC or GCC 9 or whatever, what we eventually get down to is this little file here. This is, by the way, on my Ubuntu. I think this is 18 something. I should actually check that out. But this is what I installed with WSL. If you're running on a Linux box, raw, right on the hardware, you may get a different path. If you run on the Mac, that will work as well. And by the way, most of what we're doing today can be done with modifications on a PC, on a Windows machine, on a Linux box, on WSL, on Mac. Our specific use of CC and GCC, you have to do some magic to get that to work on Windows, but it pretty much works on a Mac as well, and previous semesters I ran it there. All right, so we're to the point where we have this .hi, and .hi says hello and everything is good. But now we want to kind of look at this in a little more detail. So let's say instead of doing a CC, let's do a, since they're all the same, I think we can just do this. We'll do the dash, 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 and the dash, dash, dash says don't actually run this. Just tell me what you would run. And if we do that, we get this whole bunch of garbage. So there's a lot going on there. And that's too much garbage for me to parse. So let's throw this into a file garbage.txt. Just a little text file we can look at. And let's take a look at what's going on here. We can come in with vim garbage.txt. I'm trying to check whether there were any questions, but I'm having problems finding the right window. Okay. No questions, no hands raised. You guys are just either bored, silly, or eating this up. Up to you. So if we look here, okay, so this is doing, this is just some startup stuff, telling us how things are all set up. Thread model. We finally get down to running our GCC compiler, and this is the first command. So what we see here is that we see that the first command is actually this cc1 command. And there's a lot of garbage here. This gets more and more obtuse every year. So I'm just going to strip out a lot of these flags that we put in here and that we actually like to use. But here's essentially the core of the command. cc1, oops. Dang it. I got rid of the all-important source file. Okay, so here's cc1. I practiced this. There we go. Hi.c. Okay, -o. So there's the first command that gets executed. The second command is this. And by the way, this is the part that changed. Absent flags to put this step in explicitly. This used to not explicitly do the assembler stage. But there's a second command. And then here's the third command. Okay, so and one more thing. Did I already get rid of it? Okay, there we are. Sorry about that. Too much garbage to see. But we distill it down. We strip out all the garbage and all the system defines, etc. What we end up with is we actually end up with these 3 commands. So the first command takes our input file, runs some pre-processing on it, processes all our macros, and takes our input file, our source file that we wrote, hi.c, and what it's going to do is it's actually going to turn it into assembler. And it's going to put the assembler in this file here. The second phase is going to take this assembler, and it's going to, right, this is the same file, so they're linked together, and it's going to assemble that into an object file. An object file is the actual code that the computer will recognize. It's not yet in a program because there's the possibility that we have to pull multiple things together. And this last phase, this collect2, pulls this all together into the executable program hi. So even in this really simple system, what we actually have is we actually have a multi-tiered kind of build system that actually gets executed, right? So we come through, and now I'm trying to find that screen. You would think, here it is, it's right behind. Okay, so, even in that very simple one-line compile, gcc hi.c-o hi, there's actually a string of things that go on. And these string of things are all pulled together by this master program, GCC, that knows how to run them and knows how to transition between phases. And the cool thing is that by the way this is pulled together, right, we can have whatever front end we want. This is the front end for hi.c for a C file. We also have a front end for a C++ file. We can have a front end for any language we want, and as long as any compiled language we want, and as long as it takes it and takes in the source files and converts it to assembler, well, the rest of it, the assembler and the linker, don't actually have to change because we've built this build system that takes in a source file, runs a preprocessor, a first step to convert it into an intermediate representation, in this case assembler, and then pulls that together into an actual executable program. So we can have as many languages as we want, and all we have to do is kind of swap out this CC1 part. Okay, so this allows us to do some stuff, right? And in particular, as we kind of get our programs more mature and more complicated, this is going to be a completely synthetic exercise. You would never go through the hoops we're going to go through to make things arbitrarily complex. But let's say we don't like having this printf hello in our main file. Perhaps we have different printfs we want to swap in there. Maybe we're writing a helicopter on Mars and the printf is different because it has to print on a CRT, a million miles away or something. So we may want to swap out this printf, and to do that, what we're going to do is we're going to isolate. The main code can stay the same, but we're going to isolate what we're going to use for our header file, for our print file. So we will just do something like, we'll create a hello.h file. So we'll do hello.h, and the hello.h, right? You remember that what we do in H files is we take our definition, didn't work that time. Okay, we take our declaration, we tell the program what it's going to look like. So we're going to have a hello function, and it's going to take a void. That's all we're going to have for the declaration of this function. And then what we can do is we can create a hello.c file. And in the hello.c, we put the actual guts. So we include our declaration. right? We include our declaration, hello.h. We include our standard IO because that's the libraries we're going to link in to tell us how to do our prints. And then we will just put our print statement within this hello file, and it'll just print out hello when it gets the opportunity. So, right, it's kind of an arbitrary setup, but the beauty of this is what it's going to allow us to do is it's going to allow us, if we need to do two things. We can swap out what function we're using for this to print out our hello, and maybe this is not a single line piece of code. Maybe this is a really complicated piece of code, and it's something that we want to use over and over again. It's a functionality we need to use. So this will also allow us to use it in any other function we write that wants to use it, right? So this gives us two benefits right off the bat. It's pretty standard for ways of decomposing programs. Now what we have to do is we have to go into our main, right? We're going to do that we're going to copy. I don't want to kill my hi.c, so we'll do a copy hi.c over to, I don't know, hi1.c, which, by the way, I will mistype as h1 this entire lecture. So you guys can feel free to not comment on that, but, you know, maybe play a sip of coffee game every time I make the mistake. Take a sip of coffee, and you'll be up for the rest of the night. Anyway, so now we can come in and we can change our hi.c to actually use our hi1.c to actually use our hello function. So to do that, well, we no longer need standard IO because we're not going to be calling that directly. So we can just call, we can just include hello.h. Int main will be more precise. We'll put a void in there, although we don't really need it. And then we're not going to print out directly. We're just going to call our hello function with no parameters, and somehow there, that looks better. Does that look right? That looks right. Okay, so now what we have is we have two source files. And we can come in again and we can do the same thing, right? We can do a cc and we'll kill that. We'll make this hi1. We'll make this hi1.c, right? And this isn't going to work because it's going to give us an undefined reference. So now we can just come in here and we can put our hello.c in here as well. So now we have a slightly more complicated example. Still not atrocious, but a slightly more complicated example. And what we can see is that now we're starting to and if we do /hi1, right, it'll still work. And then we can look at what actually gets accomplished. And, well, all right, so we have the same problem with me having to go through and parse this, which seems like an inefficient use of our time. So I did check this out, but we're going to go back. We're going to cheat a little bit, right? So when we do that, this time, what we find out is we have something that looks like this, right? We have to compile hi1.c. We have to take it and convert it to our intermediate format, which is assembler. We'll take the assembler and we'll convert it to another format, this time the binary format for our actual chip. So this will actually be the object code. And then we do the same thing for hello.c, right? We take it and we convert hello.c, our auxiliary file, our helper file. We convert that to assembler. We assemble it into object code. And then this time the collect does a little bit more because it has to take the temp files, right, from hello.c and the temp file from h1.c, and it has to pull those together into one compiled program. So now we're talking about with two source files, we're talking about, you know, 5 different steps to get from our two source files to our something we can actually run. All right, so this is a little bit more complicated, but again, GCC can pretty much handle this, and we get the ability to kind of pack in this hello.c. We can have as many versions of hello.c as we want, and we can share this specific version of hello.c with as many programs as we want. For example, we can come in here, and let's just say we take and copy hello h1.hi1.c to hi2.c, and then we edit hi2, right? We can come in here and we can take this and we can maybe call hello twice. And we can do the same kind of compile line, replacing all of our high ones with high twos. So now we're actually sharing that hello1.c file, and we can do it to do something completely different that no one has ever thought of before. And we have to get rid of our hash marks in order to actually generate the code. Okay, so now something completely different. Instead of printing out hello once, we print out hello twice. Again, not completely original or useful, but it's something. So yeah, so that brings us to kind of this stage, right? We're now able to, we can compile hello1.c, we can compile hi2.c, and we can run them both. And when we come in, right, what we're doing is, well, this one is 5 steps, right? Compile, preprocess, assemble, preprocess, assemble, and then link it all together. That's 3. Preprocess, assemble, preprocess, assemble. 5, right? And then another 5 to do the exact same thing here. And what we should start thinking about is that, well, what happens with this hello.c? Is there any difference between the first time we compiled and assembled this and the second time? And the answer is obviously not really. So now we're starting to waste work. And we can still do this. It's still pretty efficient with GCC. But as our programs grow and as we get more and more of these shared files, what we're going to want to do is we're going to want to stop. We're going to want our build system to kind of stop doing all this extra work, because it's not as bad now, but I remember days when a compile was 45 minutes, right? So you would start a compile, and then you would hope you didn't have any errors, because it was going to be 30 minutes before you got to the first error. So you would actually go through and you would be hand compiling the code in your mind while it was actually compiling, so that you could, at the end of the compile phase, have the next version ready to go, just quickly looking at the compile errors to make sure you'd caught any of them or see if there were any new novel ones that you hadn't caught. Well, I'm lazy. You can see that I often make mistakes when I'm typing things. So in the world of automation, what we'll start doing is we'll start thinking of ways to make this both less repetitive, but also more efficient, using less cycles, but also to make it less repetitive for me so that I don't make as many mistakes. So the very first thing we can come up with is maybe what we want to do is we want to take this and we want to turn it into a shell script. So what window am I showing? Right, so we can come in here and we can create a file. Right, and all we can do here is we can embed all of our CC commands, all of our compilation commands, pretty much just the way they are. And then we can go through and we can kind of execute those shell-x build.shell. We'll actually execute the build.shell. The -x says, show me what you're actually doing. So if I remove hi1 and hi2, and run out and do an ls-la, right? They're not there, so I can run my shell file, and it'll go through and it'll generate the files we want, and we can go through and execute them. And again, so now we have a simple build system. It's a little bit more powerful than GCC, from the standpoint that I don't have to enter all of the commands because I've actually encoded the commands to GCC actually in the file. So, okay, so it gives me a little closer to efficiency from my standpoint. I don't have to think about this as much. I don't have to do as much work. But I can also come in here and we can instrument this, right? And instead of using this, I think I'll just use a -v, which I think does the same thing as the hashtags, but actually does the compile anyway, right? And we can quit this, and we can actually see the amount of work we're still doing. So we've gotten over one hurdle. It's easier for me to remember what to do, but at the same time, we haven't gotten rid of all hurdles. Boy, that was a... this should be shell-x. And that was not the right thing either. Okay. And now we can look at garbage.txt. And we can see that there are, you know, if we look, there's 1, 2, 3, 4 CC1s. There are, oh, that's not going to give us a good one. AS space maybe. 1, 2, 3, 4 AS spaces. And there's one, two collects. So 10 operations to get this. Pretty much we counted before. 10 operations to actually get this compiled. So we've improved our repeatability from the standpoint that I can now I don't have to remember all the commands. I can just pop these into a shell file, and this could get arbitrarily long. But we're still wasting a lot of effort. We're doing, you know, at least with the hello.c stuff, we're building that when at times when we don't actually need to. Let me do a quick check. Any questions? Anything? This is the long part of the lecture, but we want to kind of build up this standpoint for there's a lot more going on when you're doing a build than you actually think about. Because that's an important thing. Why, you know, automating something or making something more efficient when there's not much going on is not really all that important. We want to show you that even in a very small program, even in something that's very short and very trivial, there's a lot more going on than we think. And we can improve it both by making it easier for us to specify complexity, and as we go along by making it more efficient. So, you know, we're kind of sitting right here, right? There's 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, lots of operations. This stuff is definitely duplicate. We can at least get rid of that if we're being smart. So let's start looking at that a little bit. Well, okay. So we don't actually have to throw all of these together, right? We can go through and instead of doing our, well, here, let me go back to this window. So if we look at our build file, right? Right, we're allowing our GCC compiler to have all the fun, right? It's going through and has no knowledge about what we're trying to accomplish, but what it's doing is it's doing the most straightforward thing it can to ensure that our program executes correctly. We tell it we need hi1.c and hello.c, and so it goes through and it builds hi1.c and hello.c. And similarly, excuse me, we need hi1.2 and hello.c, and it goes through and builds hello.c, builds hi2.c. It doesn't have any concept of what the state is of all of those things. So what we'll find is that as we want to have more fine control over the state of things and over how things get compiled and put together, we'll find that we'll have to take more control and make this more complicated. So the first thing we want to do is, instead of just having one command line, we're going to start off with having two. And we'll say hello.o. Sorry, instead of having one command line that links everything or that compiles everything, what we'll do is we'll start off by breaking off the hello.c. And what we're going to do with hello.c is, instead of creating, taking it and pulling it into this line along with hi.c, is we're going to say, okay, we know that there's only one hello.c file, and it's going to generate one hello.o file, and we don't actually have to recompile it multiple times. We will just come in here and we will reference hello.o in our two. We'll compile it once. We'll create an object file once. So we'll do a CC1 and an ASM on the hello.c file. And then we'll use that to generate this intermediate object file, which is generated anyway, right? We just saw that in our previous runs. So then we'll use that hello.o file, and we'll just link in that object file right in with our hi1.c, and we'll use that instead of compiling, instead of CC1ing and AS assembling this hello.c twice. So if we do that, right now we can do a shell -x build.shell, and I'm just gonna, we'll do this in the garbage again. Right, and now if we look at that, right now we take and we generate CC1 for our hello.c file, right, and then immediately after that, well, not immediately, but a little bit after that, we generate our assembler on that hello.c file, right? So we've just done that once. And now when we come into our H1, hi1, right, this time we just have the CC1 and the AS on our hi1 file. We don't need it on our hello file. We've already generated that, and instead we can go straight to our what did I do wrong here? You do actually have to tell it that it's only generating the object file. I think that'll work. Yeah, that looks much better. Okay, so I'm going to go back to the one I already transitioned out, and you're just going to have to trust me that it does what I tell you it's going to do. So this time, because it's too much of a pain to parse through that file, but if you carry out the experiment, it works. So now what we do is we do once we get the errors out, we do the CC1 with the. I missed it here too. Okay, I will fix that. There should be a -c in this line. All right, just like there is down here. All right, so the GCC, it just runs the compiler and linker internally. So it runs the compiler and the assembler on hello.c to come up with a hello.o file. This is the one representation of this specific hello.c file. And then we compile and assemble hi1.c, and then we collect that along with our hello.o. We don't have to recompile our hello.o. We don't have to run the cc1 and assembler phases on hello.o because we've generated the hello.o and we've kind of saved it away. So by saving it away, eating up a little space, we can come through and generate this, and then we can do the same thing for hi2. And what we've saved ourselves is we have a slightly more complicated build file, but it's in a build file, so we don't have to do this manually every time. Anyway, we only have to do shell build shell-x build.shell. So we've kind of hidden away that complexity, and now we're starting to get some efficiencies because now we're only doing hello once, and we want to kind of push this forward again, right? So we can take this a little further. We can split hello.c up into 2 files. I don't know why we would want to do this, but we're going to do it anyway. But it is going to show us the complexity kind of growing on our program. So now let's do copy hello.c to hello2.c. And now we will vim, and we want to copy it to hello1.c as well, I guess. And now we want to edit hello1 and hello2. And what we're going to turn these into is we're going to make this slightly more complicated. This is hello1. So we're going to refer to something and extern So we're just going to kind of break this up. We're going to define in hello2, we'll define this print hello function, and print hello is going to take a parameter, a character string. It's going to allow us to be a little bit more elaborate in our, maybe this would be an error message or something. But we can come in here, we can say print hello, and we will print out world spelled correctly. Right, and now we'll write this out. We'll go to our hello2.c, and now we don't actually need any of our definitions. We'll just do our print hello. Right, this is where the print hello function will live. And we can come in here, we can say hello, and this should be taking constant character s. Yeah, that all looks right. Okay, so now we're getting arbitrarily more complicated. We want to encapsulate this. We don't want to have to type all of the stuff in we need. So we're going to go in and we're going to change our build file, our shell file, and we will come in here and we will do, well, we'll have to compile hello1 down to object. We'll have to compile hello2 down to object. And then we may as well compile. Let's really take control of our compilation, and we will specify our hi1.o and our hi2.o. Right, and now we have to pull those all together, so we want to change this to an O and pull both hi1 and hello together. Oh, and by the way, we have hello1 and hello2 here now. All right, does that look all right? That looks pretty good. Okay, so now we're getting more and more complicated, right? And the thing here is that some things are not making sense anymore. So we can come through and we can build this. We'll do a shell-x build, and it's a multi-phase thing, and it does a lot of stuff. I'm not even sure if this is working. Yeah, it didn't work for high 1. Let's go back in there and fix this. Ah, did high 2 twice. And I'm going to take off the -v while I'm at it, because that's detracting from our ability to kind of look at what we're doing. All right, and they should still work pretty much the same as they used to. We've changed the prompt a little bit just to give some reason for having multiple redirection on the printing hello. Okay, so now let's take a look at this. This still works, right? We've created something that actually works. We now have our build.shell file has 6 lines in it, and we know that each one of these -c lines does a preprocessor, a CC1 followed by an ASM or by an assembler. So 2, 4, 6, 8, 9, 10 lines, 4 files. We create 2 programs, right? So it's not horrible as far as duplication of effort. We're not doing a lot, but we're actually starting to run into things where, we broke up this hello file and we broke it up into 2 files, and the 2 files depend upon each other, and we have to know a lot about the system. So we're having to keep track of what depends on what, and we're, if you have hello 1, you need hello 2, and that type of information. That's really what computers are good at keeping track of for us. So maybe we shouldn't have to worry about that. Maybe we should just have our output functions all lumped together in some kind of bunch where when we need one, we pull it in, and it doesn't matter how complex we make this subsystem, because it will always work, because we're putting everything that needs to work together. So now we're going to create this concept of libraries. We're going to look at 2 different types of libraries. A static library is a library where the library is included in the executable. So it's physically embedded within the executable. And it's just the same, essentially the same as doing this here, right? This compilation here. The output is about the same. But the cool thing is that at least we don't have to remember whenever we want to use this library that hello 1 and hello 2 have to go together. Instead, we can just reference the library, and we get whatever modules we need to do our print right from the library, because our H1 and H2, all they know is they have to call hello, and they don't really care what goes on past that, right? So we can come in here. Let's change our build system a little bit. It's going to be a fairly simple change. After we generate hello 1.0 and hello 2.0, all we're going to do is we're going to do this little ARQC. This basically does a quick and dirty archive, a quick and dirty library, static library. Everything, everything's linked together in the end. It doesn't change the organization of the code so much, but it does allow us to lump these functions together, hello 1 and hello 2. So now all of our print functions are going to be together in this library. And then down here, when we pull everything together, well, we don't have to know about the associations here. We can just say lib hello.a. Okay. And we're adding one step into here, but this step only has to be executed once when we change, when we compile. And after that, we get the ability just to reference as many modules as we want to stuff into that lib hello. And I think that looks correct. So now we can do our shell again. And we can see that our files have changed, right? High 1 and high 2 are now from 12, from 130, which is about now. And nothing actually has changed. They both still operate the same. And remember that these are 16,824 is the number of bytes in them. I don't know if we have enough here to make a big difference, but we're going to take this one step further. Static libraries, this executable high 1 and high 2, they both contain all of the code for hello 1 and hello 2. So all the executable part there is actually within those executable libraries, and it doesn't matter that there's 3,602 bytes in libhello.a. That really doesn't play into these guys, other than that 3,602 bytes is actually included in both of these executables. So there's one more improvement we can actually make. And the last improvement is we can come through and we can start talking about shared libraries. Oh, I'm sorry, I missed a step. The other thing we can do is we can actually look at, if we do like an ART lib hello, we can actually look at what's there. We can see that hello 1 and hello 2 are both there. The object files. Yeah, so they're that archive, that library, essentially just encapsulates our two object files. Okay, so next step. The next step is we can get one more efficiency out of this before we have to abandon our shell script. And the one more efficiency is static libraries are linked into the executable. So all the code in that static library, no matter how big it is or how small it is, gets included in the executable size. We don't actually have to do that. We can create something called a shared library, and a shared library encapsulates all the code, and when we link to our executables H1 and H2, we don't actually pull in the shared library code. What we do is we pull in a reference to the shared library code, and then when we run H1 or H2, the shared library gets pulled into memory using the linkages we set up, and it's called from there, which means that we can shrink our executable sizes, right? Because our high 1 and high 2 executables don't have to include the shared library code. And if we're shipping multiple programs using the same shared libraries, we only have to send the libraries once. More than that, we're going to change our memory space allocation, because we don't actually have to have multiple copies in most cases of the shared libraries in memory. There are some cases where it'll get pulled in if there's a conflict. But in general, we don't have to have multiple copies of the shared library in memory. So that means that multiple programs can access the same shared library resident in code once, resident in memory once. So let's take one more little step here. We're going to take our build system, our build shell, and we're going to change it from a static library to a shared library. I'm going to cheat. I'm going to copy paste this one in. Right, so that's not really all that difficult. Instead of our archive step, we're just going to do another call to our GNU library, and we're going to tell it that what we want to create is this lib hello, and we want to create that as being shared. Okay, no questions, no hands raised, nothing. Cool. Okay, so that's going to create our archive, and this archive is going to be a shared library. We're flagging it as such. We still create our high 1C and high 2Cs the same the same way. We do have to add something up to our to the modules, to the functions that are the files that are going to be in our shared group. We have to add this little f pick command that says that because we're doing a shared library, this has to be relocatable code. And all that means is that all addresses within the code are relative to the base address of the file. So we're not encoding any absolute addresses. If you're doing a shared library, you don't know where it's going to get put in memory. It's not specified by the link command, so the code has to be relative to some fixed starting point, or to some starting point at the relative to the file. So you should say some fixed address within the file, right? So this just sets it up so that hello1.c and hello2.c, when they get generated into objects, don't have any absolute references. That solves that. And then the final thing we have to do is the shared library has to be found. So we have to give it some link directives to tell it where to look for the shared library file when we actually need it. So this just basically says, it just basically tells it where to look for the shared library file, because it's not going to be within this hi1 and or hi2 executable. It's going to be elsewhere, and this just sets it up for where to actually look. Okay, I think I've got everything. Oh, I need to change this to a .so file. Okay, I think that's it. All right, so remember that hi1 and hi2 were 16.824. I didn't actually check this, so we're hoping that this actually lowers it, but it did last year. I can't imagine that it doesn't this year too. Okay, so we execute those commands. We do an ls-la, and instead of being 16.824, it's 16.680. Instead of 16.824, it's 16.680. So we've saved a little bit of space. You can imagine that there's some fixed information that has to be saved. These were not very big files, so the amount of savings is relatively minuscule, but it is a savings. Of course, on the other hand, our lib hello is ballooned up to 16.272 instead of 3.602 to handle all of the relocation and loading and stuff like that. But again, if you had more code and less overhead, relatively less overhead, this improvement would be, well, this would actually be an improvement instead of, taking 3 times the space. All right, any questions on that? Anybody doubt that it works? Remember I told you that you had to take a drink of coffee when I mistyped hi1 as h1? There we go. All right, so everything's still working. This is a little bit different if you're in OS X. The commands to compile are a little bit different. Specifically, instead of $origin, last I checked, you needed -rpath. This may have changed depending on what version you're running, but it's not overly different. And we can look at some dependencies. So we can look in here. We can say readelf. And we can look at lib hello.so, and it'll tell us, a lot of stuff, especially because I didn't do that right. We want to readelf on our executable file, hi1, and we probably want to pipe that into our grep for needed. And that'll tell us that we have 2 dependencies. For readelf, one, it needs our general C libraries, but it also needs our lib hello. That's because that's shared. It hasn't been statically linked in. And we can also, and that's different on OS X. It's O tool command I wonder if this works here. No, okay. I didn't type it in correctly, but it wouldn't have worked anyway. And what else do we want to do? I thought there was one other thing. I guess not. Okay, so